Hi, everyone. Thanks for coming to our presentation, and thank you, Neo4j, for inviting us to present today. I'm Anna Reyes, data scientist at Kinevus.
Hi, everyone. I'm Marjorie Kang, and I'm a clinical research associate for data science at Northwestern University Feinberg School of Medicine. It is our honor today to have a chance to share our pneumonia project in process to you all.
Thanks, Marjorie.
Yep.
So we want to talk to you today about how to use graph algorithms and visualization to look at electronic health records data, specifically for pneumonia patients. So this is a bit our agenda, a small introduction of who we are, the larger goals of this project, the type of data that we're working with, and how we created a Neo4j patient graph. And then a bit about our preliminary analysis, how to visualize a single patient journey, how to group and identify similar patients with similarity algorithms and graph embeddings, and a simple risk model to identify vulnerable patients, and what we are hoping to do for our next steps.
Great. So I'm going to first introduce what is the backend story for this MIMIC project. So currently, I'm working on a multi-year pneumonia project called SCRIPT. So what SCRIPT means is it is successful clinical response in pneumonia treatment. So as we can see here, our data sets including REDCap survey data, EHR, clinical trial information, and mouse models. And we also collected genomics, metagenomics, and transcriptomics, these multi-omics data sets. And our goal is to integrate this rich data source to help us better understanding why a severely ill pneumonia patient is likely to recover or maintain the status or unfortunately expire. So currently, I've already built a graph database for about 670 patients for the pneumonia cohort. And we did a bit community detection and classification on pneumonia types. And by pneumonia types, so what the clinicians adjudicated are the types including community-acquired pneumonia, also called CAP, or hospital-acquired pneumonia, also called HAP, or ventilator-associated pneumonia, that is VAP. So we try to classify the patients and see if the clusters match those three types of adjudications. And we also tried to use the graph embeddings to predict whether a patient is likely to recover or unfortunately expire. But what we found is the graph embeddings didn't quite improve the accuracy of the classification or the prediction of the patient outcomes. So that's why I looked into MIMIC, which is a larger and a mature ICU database. And we were hoping that we can use these MIMIC data sets as a training set and then bring back what we've learned to the SCRIPT study and to help better assist the clinical decision. So I will pass on to Anna for more details.
Thanks, Marjorie. So I'm data scientist for Kinevus. We're a young company in San Francisco, and we developed GraphXR. And GraphXR is our our browser-based graph visualization and analytics tool. We work with companies in several domains such as counterterrorism, financial fraud, bioinformatics, and my job is to merge deep learning, machine learning, and graph technologies to make sense of interconnected data in GraphXR. So what is our goal for this project? We want to use there's three big major aims. The first one is descriptive. Let's help build a dashboard to help clinicians treating pneumonia patients be able to access and digest the large amounts of information that you find in electronic health records about a patient's clinical history. The second aim is prescriptive. We can help with graph similarity, graph embeddings, help doctors identify similar patients to the one that they're treating now. And if we can show them, what have other doctors done in terms of diagnoses and procedures with similar patients, we can suggest potential care paths. And lastly, predictive. We want to build a risk model that helps you identify at-risk patients or vulnerable patients. For example, the rate of 30-day readmission for pneumonia is on terms of 25%. So that's quite high. If we have a risk model that can help us identify vulnerable patients early, we can perhaps intervene before and have better health outcomes. So the data that we're working with, the Medical Information Mart for intensive care. This is a data set of around 40,000 patients that were admitted to the Beth Israel Deaconess Medical Center in Massachusetts. This data was collected both from two sources, the electronic health records from the hospital and also the bedside monitor that tracks vitals. It's quite complete, as you can see in this slide, and it has been de-identified. So names and addresses have been removed and all the dates have been shifted randomly into the future. So the data for a single patient remains internally consistent in terms of the timeline, but two patients, the only thing that we can know about them is whether or not they went to the hospital, they were admitted in the same 3-year window. So the temporal sense helps de-identify the data. But we're talking about very high dimensional data, right? Because given a set of specific diagnoses and procedures and a time window and location, it's not that hard to potentially reverse engineer and identify the data again. So actually, we won't be sharing any of the raw data from our project, only the analysis. And the only way that you can access the data is by doing a human subject research certification module. So we filter the data set. We're not working with all 40,000. We want patients that have gone at least one pneumonia diagnosis. And then we want to look at the visits 1 year prior to the onset of the first pneumonia and 1 year after the last pneumonia incident that they had. Then we connect in our patient graph all the diagnoses and procedures associated with those admissions. These are both at the ICD-9, or rather, the data contains both ICD-9 and ICD-10 diagnoses and procedure codes. So we standardize those to ICD-10, and they also have diagnoses at the 3-digit, 4-digit, and 5-digit level. So we also just, at least for a preliminary analysis, we roll them up into 3-digit level. So it simplifies things, because if you're talking about 13,000 ICD codes at the 5-digit level, and it becomes 1,500 at the 3-digit level. So it's a way to kind of simplify for our preliminary analysis. So here's some example code of how we're creating our patient graph in Neo4j. So a lot of the data munging we did in Python. So we're using the Neo4j Python driver to connect to the Neo4j server. Once we've cleaned our data, filtered our data, we save that CSV file in the import folder on the Neo4j server. And we're using here the load CSV syntax to generate the patient nodes. So here, for example, we have patient nodes with gender, age, date of death, and there's 7,100 patient nodes. Then here's an example for creating admission nodes. We create a constraint to make sure that we don't duplicate admissions. And because we have a larger number of admission nodes than we did patients, I'm using the periodic commit syntax, because in that way, it's going to load 500 observations at one time and commit those to the database instead of loading the full data into memory and potentially crashing the server. And then lastly, we create a relationship between the patient nodes connected. Each patient has several admissions. So we connect a patient to their admissions. That's 41,000 connections. And we use the same syntax for creating the diagnosis nodes and the procedure nodes. And we have the resulting graph schema and the summary statistics here. The admission nodes are also connected to each other. So each admission has a next relationship to the following admission in time. And later, when we create the similarity graph, admissions are connected to their more similar admissions.
Great, thanks, Anna. So now we got the database on the server. So it's time to do some exciting exploration. And here is an example of a so-called local pattern matching. And I did a quick poll of the patients that I'm interested in that developed both VAP and CAP during their multiple hospital admissions. So what we can see here, the purple nodes are all the admission nodes surrounding the patient node. And most of them had a couple of ER visits. And we can see that they indeed share the ventilator-associated pneumonia and one of the very commonly caused community-acquired pneumonia, that is Streptococcus pneumoniae. So now we know that what it looks like and what we're going to check on specific patients. Now I'm going to explore in another way instead of using Cypher to explore the patient journey and visualize it. So this is a preloaded view, but I'm going to start from fresh and show everybody how we reach that visualization on the patient journey. So I preloaded this patient because for privacy protection, and I only showed the gender and the anchor year. And now we are going to expand this node and see what admissions and diagnoses that these patients have. So there are a couple of ER visits and transfer from other hospitals. And we expand again to see the diagnosis. So this patient, we can see a very dense diagnosis just in one admission, and we will keep expanding until we get the full landscape of all the diagnoses. Obviously, at this time, it's beautiful, but it's not that digestible for a data analysis point. So I'm going to limit the number to the major diagnosis for each is got separated. And now I'm going to select the patient node that allow me to trace the neighbors. Here we go. So one hook away and the other one. Now we got all the admission and diagnosis selected. And we're going to select the visible nodes and do a reverse selection and delete all of them. Now we got a much clearer graph. And now let's adjust a little bit on the layout and I also want to order by the admission time. So we'll know how a patient is transferred from one admission to another. And I'm going to expand. Here we go. Yep. Now the view is much clearer, and just to be sure, I'm going to show the next relationship, so it's more clearer that which admission is the previous one and which is the next. And we can see that indeed this patient had a couple of shared diagnoses of pneumonia due to Klebsiella, and then he developed VAP, unfortunately, and then his last admission had a diagnosis of sepsis. All right, so this is a very simple demo of the patient journey visualization, and I'm going to head back here. Okay, to our next one. And similarly, we can see that we can start from a diagnose node and explore the admission and to their procedures. And we can do a degree centrality calculation, and we can find the commonly shared procedures. And one interesting one we found that called closed biopsy of bronchus. Is actually this is not a common procedure among pneumonia patients, but rather for lung cancer screening. So that helps us to think of the hypothesis that the lung cancer patients might have a higher possibility of developing VAP. So I will now pass on to Anna for more global pattern matching discovery.
Thanks, Marjorie. That looked great. And I can also see a couple of questions coming up in the chat. So for Rifayat, explain further how predictive analysis works to identify at-risk patients. So that's a section that's coming up further at the end of the chat. What is the input data format for the patient data from Dagmar? It's in CSV files. There is an OMOP version of the database, but we're not using that. And for author, did we also add lab observations? Not yet. We are working just with procedures and diagnoses for now, but there's a wealth of data in the database that we haven't added yet. And how do we integrate the multi-omic data? Not here. That is more on Marjorie's script project. So this is an earlier stage. We're at a very earlier stage with this MIMIC data. So let me talk now about the patient similarity graph. So here is some code to create a cipher projection, right? Because I want to create, I want to identify admissions that are close together. So these are all the index 0 for pneumonia admissions. So this is the first admission that a patient has had a pneumonia diagnosis. So this is the syntax to create a cipher projection. The first statement lists all the nodes that I want. So this will be admissions connected to their diagnoses, because the way that we'll define how two admissions are similar is how many diagnoses do they have in common. And then the second statement brings the diagnosis relationship into the cipher projection. Trying to change slides, but it's not. There we go. No, that went too far. Right. And then we use the Neo4j graph data science to create a similarity relationship. So this is the node similarity, the Jacquard similarity algorithm. So for two nodes, if they are both connected in total to 20 diagnoses and they share 10, then they will have a similarity ratio of 0.5. So here I'm saying if they have lower than that 0.1, don't create an edge. So what this will do is for every 2 admission nodes, it will create an edge, and the weight of that edge is going to be the similarity score. So we can see that we have 23,000 similarity edges between 2,000 and 300 admission nodes. So here's a little bit more of GraphXR. So I've loaded the similarity graph that we just created with the Graph Data Science plugin for Neo4j, and these are the nodes connected with the similarity relationship. So this is just a simple force layout that has automatically already clustered into 2 camps. The patients that went home after this admission and the patients that expired during this admission. And we are focusing, and this is a bit about already the risk analysis, because we want to identify the most vulnerable patients. And we decided that the best way to start going about this is to compare the most different groups. So this is based on the discharge location variable, and discharge location actually has about 7 different categories, because when you're discharged from the hospital, you can be discharged home, you can be discharged into a hospital, into nursing facility, into hospice care, or at the other extreme, you aren't really discharged, but you expired, right? And we thought, well, if we can build a model that, it'll be the easiest thing to do is to differentiate between those 2 extremes. So this is just, a force layout of these admissions. And what we can do is we can add do some community detection. So I go into the algorithms panel and choose the Louvain algorithm. So now each node has a Louvain community ID. So we can color by those now too. So here you can see the different communities. Here's one, here's another one. And the one that I find most interesting is this last one that's all the way out here. So my next step is to see how are these patients so different from the rest. So let's take the next question I want to answer is, okay, in each of these communities, what is the share of patients that have gone home versus expired? So let's create a new node. If I go to transform and extract, I want to create a new node from the Louvain community ID. I'm going to set this as key and run. So now I'm going to have, I think it's, 9 different nodes, and these are the community catch-alls. So let's go to layout and set these in a grid. And then expand a bit. And now I want to order all the admissions around each of their Louvain community ID in a ring. Ordered by the discharge. Nope. Ordered by discharge type. There we go. So let me focus, and if I take away the edges, we can see better. Here we go. So this is almost like if I color by discharge location, there we go. These are the communities that we identified with the community algorithm. And you can see that the orange nodes are admissions for patients that were discharged to go home, and the blue ones are those that expired. And this is almost like a pie graph visualization, because you can see very clearly here for each of the communities, the proportion of patients that were discharged versus expired. So a next step in this analysis would be, okay, for example, what makes the patients in this in one of these communities different from the others, right? So in that case, we would start looking at the procedures and the diagnoses. Going back to our slides. So we can do the same analysis that we just did, but with Cypher on Neo4j. So here's the Cypher projection for an admission similarity graph. So I want to project all the admission nodes and the similarity relationship between them. And then we can use the data science library to run the Louvain community algorithm and write to each node a new property that is the community ID. And then this is the same. Oh, these slides are not cooperating. This bar graph is essentially the same visualization as the donuts that we just looked at, right? For each community, what is the share of patients that have expired versus gone home? Because when a patient's community membership then will be related to his risk analysis. The next example is using graph embeddings algorithm to also identify similar patients. So here we're using the fast random projection algorithm. And what's really interesting about this graph embedding algorithm is that not only does it take into account the graph topology, so which nodes are connected to which other nodes, but you can also add feature properties, node properties, as a way to calculate node similarity. So here we added age. And one of the hyperparameters for this algorithm is how much should the algorithm weigh topology versus node characteristics. So that's something that you can tune for and choose to see what's the best performing parameter. So once we, with this code for each admission node, then we're creating a embedding vector of dimension 128. So if we want to visualize, well, okay, so how does this similarity embeddings look like? We can use a dimensionality reduction algorithm, in this case, uniform manifold approximation. And then we generate a 2D view. And you can see that these embeddings are also capturing quite well that separation between patients that are discharged to go home versus those that expired. And you can even see, and I haven't double checked this, but you can see this little tail sticking out here, which I think is the same group that we saw in the GraphXR view, that was like that little community sticking out. So these are two different ways to kind of take a look at the same idea of identifying similar patients. And this is the start of our risk modeling. So the idea is, if we build a simple model that predicts whether a specific patient, given some of his demographics and given the diagnoses from that he was assigned at that admission, can we predict whether he is discharged home or expires? So here are some of the variables, the explanatory variables: simple scikit-learn, linear model, logistic regression. Here we do some tuning for some regularization parameters. And finally, this is our performance, and it's not bad. We're 96% capable of identifying those that get discharged, and around 90% able to identify who expires. So that's not bad. This is a simple model. And the logistic regression, as you know, it gives you a binary prediction, right? Discharge or not, but you can actually set it to give you a probability. And this could form the basis already of a vulnerability score, because the higher your probability, the more likely you are to expire during admission. So we can kind of flag that to the clinician on a dashboard, and they can, think about intervening. These are, because we're working with a linear model, then we can very easily take a look at the variable importance by just looking at the magnitude of the coefficients. So here are the top positively predicted variables. And actually, we realized we didn't know that encounter for palliative care and do not resuscitate are considered diagnoses. And obviously, once you have that, then you're, expiring. So it's a little bit cheating to have those as explanatory variables. But for example, here's the ventilator dummy. If you had a ventilator incident that you needed to be put on a ventilator, then obviously the probability that you will expire increases. Age here is also an important predictive variable. The older you are, the more likely you are to expire. Whether your admission type was an urgent type of admission. All of these are diagnoses that are associated with a higher probability of expiring. The next graph is the top negatively predictive variables. So, for example, if the type of admission is a walk-in or self-referral, then that's less likely to expire. right? So this is to show this not only to the clinician, but potentially even to the patient, then model transparency and interpretability is quite important, especially in a healthcare setting, because if you don't explain how a model has reached its conclusions, then you might not have trust and uptake of the model from the populations that you're trying to serve. And our next steps, trying to look at the comorbidity graph, diagnoses that co-occur together. Use Neo4j and GraphXR also has a JavaScript coding component to create dashboards. So all these piecemeal analyses that we've shown you tonight together can help make a dashboard, or at least it's the start of clinical support tool. And Marjorie, if you want to talk about this last point.
Yep, thanks, Anna. So yeah, since for the script datasets, as I described earlier, that we did some exploration on a shared diagnosis subgraph. And based on that subgraph, we did some basic graph algorithms exploration, like Louvain algorithms on the community detection. But we weren't able to find any clinical meaningful clusters that is linked to the CAP, HAP, or VAP cohort. So we were thinking that one thing is because these patients are highly identical. They all take similar medications and go through similar procedures, and they have similar diagnoses related to pneumonia. So we were thinking that using these larger data sets, and we can use it as a training data sets. And once we got the features selected and algorithm trained, and we can apply back to the script cohort to compare with our real patients' outcomes. And of course, ideally to assist the clinical decisions to improve the patient outcomes.
So I see some questions. Let me just move to our last slide, which is really just acknowledgements and thank yous. Oh no. Yes, shout out to the people that helped us.
Yep.
And yes, now let me take a look at some of the questions. Yes, can we share the link for this demo? We will. Thank you, Alexander, for saying that this is cool. Why did we choose the admission diagnosis? Well, this is so, and I think this is related to also Sri's question. How was this used in operational decision making? So this is still very preliminary work. We were hoping to be further along in the project, but it was harder than we expected working with this data. So this is still quite preliminary and is obviously not informing any clinical decisions at all, because it's all very simple just yet. But we're hoping that eventually it will lead to something like that. Let's see what else. Mark asks, for similarity, could you have done the same with other algorithms? Of course. And actually, what we did so far is comparing, what is the best way, a similarity of the Jacquard measure, the graph embeddings. There are several graph embedding algorithms that we could try. So this is all still very exploratory. Wayne Lang asks, did we use the embedded features and do the regressions? So that's one of our next steps, to use the embeddings as an input to the logistic regression. And then Jeff asks, how does this integrate with FHIR resources? I don't actually know what those are. Marjorie, do you know what FHI resources are?
Yeah, so I'm not an expert in FHIR, but I think it's a like fair and kind of for fair data sharing with the protection of the data security, but still to maximum the reusability of the data sets. So yeah.
I think that is taken care of by the project that shares the mimic data, Physionet, and it's affiliated with MIT. So I think they've definitely given that a lot of thought, and this data set is widely used in this type of analysis.
Yep. Yeah, and I can add to that. So I'm less familiar with FHIR, but I'm more familiar with OMOP. And I think thanks to Marilyn up there, that she shared a link that includes the code that I generated for building the script database. So I think someone also asked a question that, did you integrate any labs and medication information into the graph? So if you're interested in that, you can check out that GitHub repo and see how I transformed OMOP, which is also a common data model to facilitate data sharing across hospitals and institutions, and how I make that OMOP common data model for script cohort to Neo4j graph database.
And then Wen Liang's question of how do we choose the number of dimensions of 128? I don't know if I already answered that, but so that is something that you can tune. That is also a hyperparameter, 128, 256. We didn't do tuning so far, but we would definitely do that as a next step. Yeah, I think thanks everyone for being here and for these great questions. And thank you, Marjorie, for coming to do the presentation with me. It's been great collaborating with you.
And thanks to everyone. Yeah.